सादर नमस्कार, सुस्वागतम, अभिनंदन, केम छो, जय श्री कृष्णा, वणकम, आदाबाज, सत श्री अकाल, राम राम, राधे राधे, ए वेरी गुड आफ्टरनून। मैं अनिल भारद्वाज आप सभी का पीआरएल के अमृत व्याख्यान के 108वें अध्याय में स्वागत करता हूं, अभिनंदन करता हूं। आई अनिल भारद्वाज very warmly welcome you all for the 108th PRL Kamrit Vyakhyaan. We started the PRL Kamrit Vyakhyaan as a part of celebration of PRL's 75 years of establishment. It coincided with the country's Azadi Kamrit Mahotsav, celebrating 75 years of independence of India. And this was meant to celebrate the rich legacy and history of the contributions of PRL to physics and space sciences, as well as a tribute to Dr. Vikram Sarabhai, who established PRL Kamrit Vyakhyaan, who established PRL in the year 1947. So we started this series on 4th of August 2021 with a sankalp that every Wednesday at 4 p.m. we will have PRL Kamrit Vyakhyaan. We continued 75 episodes of uninterrupted PRL Kamrit Vyakhyaan. And after completing that in January of 2023, we started the monthly series of PRL Kamrit Vyakhyaan known as PRL Kamrit Vyakhyaan 2.0. And that is continuing uninterrupted every month. Today, that is 25th of September 2025, Thursday, 4:30 p.m. We have yet another very distinguished Vyakhyaan Karta with us, Professor Wing-Huen, who is professor at National Central University in Taiwan. And he is going to give the Vyakhyaan on From Cosmic Dust to Venus Habitable Zone. We warmly welcome Professor Wing-Ip for this Amrit Vyakhyaan and thank him for agreeing to our invitation to give this PRL Kamrit Vyakhyaan, 108th PRL Kamrit Vyakhyaan. I now request my colleague, Professor Pallam Raju, to kindly introduce today's Vyakhyaan Karta, Professor Wing-Ip, to the audience at the WebEx, as well as those who have joined us live on the PRL's YouTube channel. Over to you, Professor Pallam Raju.
Thank you, Professor Bharadwaj. And it is indeed a great pleasure and honor and a privilege for me to introduce today's Vyakhyaan Karta or speaker for the 108th PRL Kamrit Vyakhyaan, who is Professor Wing-Huen Ip. Professor Ip received his undergraduate degree in physics from the Chinese University of Hong Kong in 1969, followed by graduate studies in the United States, earning his PhD from the University of California, San Diego in 1974. After postdoctoral work, he joined the Max Planck Institute for Solar System Research in Germany, wherein he served for close to 2 decades before moving to the National Central University in Taiwan. At NCU, he has held several leadership positions, including the Dean of the College of Science, then Vice President and Vice Chancellor of the University System of Taiwan. Professor Ip's research spans cometary physics, planetary atmospheres, solar system evolution, and exoplanet sciences, with cumulative publications of over 500. He has played a key role in many landmark space missions, including the Gito to the Halley's comets, Galileo to Jupiter, Cassini-Huygens to Saturn and Titan, Mars Express Rosetta to Comet 67P, among others. In recognition of his outstanding contributions, he has received numerous honors, such as being elected as Fellow of the American Geophysical Union, member of the International Academy of Astronautics, and an academician of the Academia Sinica. He has also been awarded the NASA Exceptional Public Service Medal, the AOGS Oxford Medal, the Gerard P. Kuiper Prize of the American Astronomical Society, and most recently the Presidential Science Prize of Taiwan in 2023. Beyond his scientific achievements, Professor Ip has been a leader in the international scientific community as the founding president of the AOGS, that is Asia Oceania Geosciences Society, and served as the European editor of the Journal of Geophysics, Space Sciences, executive editor of Planetary Space Sciences, and editor-in-chief of Advances in Geosciences. It is indeed a great honor for us to have Professor Ip talking to us on a very exciting and a interesting topic. The title of which is From Cosmic Dust to the Venus Habitable Zone. With this few words, I invite Professor Ip to share with us some of his excitements and views on this interesting topic. Professor Ip, the stage is yours.
Yeah, thank you so much. Thank you so much. It's indeed an honor and privilege for me to be able to be accepted to give a talk at this conference. It is a seminar series. Can I have the first slide? Can I have the first slide? Yes, thank you. So I must confess that I learned more about Venus from your Venus conference than any other place. Today, if not because I was invited by Professor Yayish Pabeli to give this talk, there's something that I would never have thought about, I would have just put it aside. But now that I'm going to tell you, so that I'm saying this because I am really not an expert on some of the things I'm going to say. But as you know, that the Venus is a really exciting place, to explore, and I'm very happy that India is taking the lead in this next wave of Venus exploration. Next slide, please. So this is basically my overview. I will just go over the physical structure and perhaps the origin of the interplanetary dust and hence the zodiacal light within the inner solar system about 1 AU to the sun, and then and how this interplanetary dust particle will interact with the atmosphere of the Earth and Venus, and that's what we call meteor info. And then we'll come to the recently very interesting topic about the Venus cloud sample return mission, because there's something might be very interesting happening there, and perhaps that's why you're also interested. Next slide, please. So first about the zodiacal dust cloud. The dust cloud is a diffuse distribution of dust particle, micron size or larger, and they spread around like in a flat disk. Part of this dust could have come from asteroids, in the main belt asteroid between the orbit of the Mars and Jupiter. But perhaps most importantly, they come from comets, because several prominent strong meteor streams, they are found to be associated with comets. And the reason being that for those comets that they come closer to the sun, heat up, they would their eyes would sublimate, and then producing a dust cloud. And with the dust cloud, the dust particle will drag, and then because of the solar radiation effect, and those dust particles will be blown anti-sunward, hence forming the dust tail, as you can see from this picture. In this picture, actually, you see two tails. One is the dust tail. You could recognize it. It's a rather broad and then a little bit curved. And the other one is the plasma tail. It's narrower. And if you have a color, you have a telescopic color, you can see it's actually emitting in the blue light, in the blue emission. For the dust cloud, it's more yellowish because it basically reflects the solar radiation. And in the cometary dust cloud, we found that we know that there are lots of micron or 100 micron to 100 micron dust particles, and they live in the nucleus, and then start to move more or less around the orbit of the comet, and then still around the sun. And hence, in the solar system, we have several such kind of, comet, we call it comet meteor complexes. Next slide, please. And so the light, what happened was that when at night, we look up, and on clear night, and if you have a sharp eye or with a telescope with long exposure, you can see that just beyond the horizon, you could have a patch of brightness like this. Yeah, and those are what happened, when the dust particle in the so-called cold cloud reflect the sunlight, because they tend to orbit around the sun. Therefore, most often you see them when the sun set. Yeah. This kind of dust cloud, its structure and its behavior have been studied since long. And firstly, by just looking at the scatter light what you saw in this picture, and or by the emission, the infrared emission, because the dust particle hit by the sunlight have a temperature maybe 100 degree K or within 150 K or more, and they are in the infrared wavelength. Hence, it's best to study them in the infrared wave range. And there you have, in the past, you have IRIS, you have Kobe, you have Spitzer and Akari, those space telescopes which are operating in infrared wavelength. And then, of course, you could also study them by correcting them by dust detector. And this we have in the past, we have the famous Helios, the German mission, which just basically study the dust detector business. And then you have the Galileo with the dust detector built by the same German team. And then you have the Parker solar probe. Next slide. Now I want to say a few about the back up to the, yes, this one, about the Parker solar probe, because Parker solar probe, as you know, come very close to the sun, to within about 8 solar radii. The purpose is to study the sun, the solar wind, the origin of solar wind, and the heating of solar wind of the corona. And so it does not carry a dust detector. But then how does it detect dust particle? Interestingly, when it comes close to the sun, it starts to see a lot of impact, dust impact. On where? On its antenna, on the plasma wave antenna, on its spacecraft body, and creating bubble, plasma bubble, because they are hitting the spacecraft at high velocity. So, and then hit, they generate some vapor. The vapor, it has an ion electron, and that way they create electromagnetic perturbation. So the instrument, the plasma wave instrument, measured this. So over the years, and the team has accumulated enough information, experience of knowing that, and can tell, the size or even the mass of the particle hitting the spacecraft to a certain extent, not precisely, but I think that way they can tell now that how the dust particles surrounding the sun, from maybe a few solar radii to 0.5 AU or more, how that look like according to their model. Okay, next slide. And then theoretically, as we have said earlier, the dust particle, the so-called light, they originate from the cometary dust coma, right? Hence, theoretically, in principle, you could just we know all the comets, the short-period comets in the moving around the sun, and hence we could build a model, assuming that once the comet come close to the sun within a certain distance, they will start emit the dust particle, and hence you use those propagation rate, the rate of distribution of the propagation rate, to construct the dust density. For such a small size particle, micron size particle, they besides gravitation, solar gravitation, they are affected by another force which is non-gravitational, which is the solar radiation. Yeah, and effectively we call that Poynting-Robertson effect. How does that work? It means that when the photon hits the dust particle, the photons would be re-emitted. But because the dust particle is moving in Kepler orbit around the sun, so there's certain relativistic effect. That relativistic effect adding together and would allow the dust particle to lose energy and spiral inward. So the next slide. See, you can see this. So that if a dust particle is produced, say at 1 AU or 2 AU, and because the Ponton-Robinson effect over the time, it will spiral inward, and at the end, if the particle does not hit the planet or destroyed it by one way or the other, it will come close to the sun. Until when? Until when the temperature is so high because of solar radiation, the material like rock or iron would evaporate, would sublimate, and leaving nothing. So therefore, from the observation and from the ground-based observation or from the there's a suggestion. I think that the model says that there will be a whole dust-free zone surrounding the sun, about maybe 5 or 10 solar radii, and then beyond that, you start to have particles, larger particles, which have not been destroyed by thermal sublimation yet. Yeah, so that is interesting, isn't it? Yeah, because the point is this: for those particles come close to the sun, they sublimate or they got broken up. They form nanoparticle. Those nanoparticles will in turn be accelerated by solar radiation and produce in very high speed particle that we call the beta meteorite. And presumably the Parker solar probe would have been hit by those nanoparticles also. Now, how come, why do we talk about this, about the zodiac light? The reason being that those meteors, we say that they come from the comet most of the time. And when the Earth's orbit goes through, the meteor stream, cometary meteor stream, they would be bombarded by such a tiny particle. And you can see the picture here. The upper picture tells you that that's a famous picture because there was one time presumably the Earth just went through the center, the densest part of meteor stream. Yeah, maybe Leonic. Yeah, and then there are thousands of of foreign stars, and people producing such a memorable picture. But on the other hand, outside the meteor stream, still you can see meteors sporadically because some of the dust are not necessarily concentrated in the meteor stream, but sporadically dispersed over the solar system. So you have two types: one's a meteor stream associated with comets, and the other type just can be coming from asteroid, from other things. Yeah. One of the, I would say, the important key job of the meteor scientist is to determine, how much dust would be delivered to the Earth, to the Moon, and what kind of composition, right? What kind of structure they might be. And can I have the next slide? Yeah, how do we learn about the meteors? One of the traditional ways to look at the meteor stream, meteor when they falling through the atmosphere. Because those dust particles, they could be micron, millimeter size, or even larger, right? And but they penetrate into the atmosphere at very high speed, 10 kilometers per second, 20 kilometers per second. Such a high speed at the beginning, those meteor solid bodies interacting with the atmosphere, and the friction is very intense as you're moving into the denser part of the atmosphere. The heating will be stronger and stronger. To a certain point, you see that on the left hand side, on the right hand side, you see this picture telling you that at the beginning, the particle which has the kind of most reflective volatile metals like sodium would come out, would sublimate, evaporate, and then come to the next one, and then come the next one. So that way it means that when the meteor comes in, it delivers its composition, its constituents into the atmosphere. And for water, of course, evaporate and it mixes with the atmosphere, right? And you don't really can tell this is from comet or from meteor. But for those metals, because our atmosphere doesn't really carry metals, so you can see that the living, that's where I think at least for the Earth atmosphere, we got this minute amount of metals from meteor infall. And in the insertion, you can see also that there's a density distribution of the ions in our atmosphere. You see in the ionosphere, there's a layer, a thin layer. The thin layer coming from the sodium atoms. That has been the subject of investigation for a long time at the beginning when people start to learn about ionosphere. So next slide. And one way to do is actually when the meteors infall and you have a very sensitive spectrometer, then you take picture, you see this line emission from different elements, metallic element. You can recognize magnesium, right, sodium, and this and that. So what we learned is that what we want to remember is that our atmosphere gets metals, those small amount from the meteor infall, and they will be distributed along the way from 100 kilometers all the way to maybe to 50, maybe even to, if the meteor is larger, to 20 kilometers. Yeah. Okay, next slide. Another way to study interplanetary dust particle is if you have a spy plane, do it. So like the NASA got a spy plane U2, and then they flew it to 20 kilometers in the stratosphere. And there's Professor Don Brown from Washington University St. Louis. He was famous. He did a famous experiment that you have a dust collector hook onto a U2 and just sweeping the dust particle into his collector and bring home and look at them, study them. So one of the sample you can see here is very fluffy, right? And even after going through the atmosphere, and then you do analysis for it, and you find you can sometimes you see some very tiny particle, and with a special isotope, and we think that they are coming from the interstellar space. So that means that our solar system could be partly made of interstellar material. Now, this slide tells us just that comparing the electron density, ion density, daytime and nighttime of the Earth. And of course, you see that the nighttime, the ionosphere, you might say, collapse because there's no solar radiation, no photoionization to produce new ions. But then ions will be gradually, but in particular the molecular ion will gradually disappear because of dissociative recombination with electrons. And so took just a few hours of the ionosphere, the night side just collapsed. The next slide. But then you note, I'm sorry, going back, going back one slide. And if you notice this one, this picture, you see there's in the bottom of the night side ionosphere, there's the layer. There's the, we call it spread E. There is one layer made up of metallic ion, in particular sodium. Yes. So from there, we know that, that has to come from meteor. Yeah, the impact, particularly when during this meteor shower, that this spread E layer would be stronger. All right, next slide. Then we talk about, just now, we talk about Earth's ionosphere interacting with the meteors. How about Venus? So there are a number of scientists, care about Venus, and they want to do model, studying how the micrometeorites or interplanetary dust will interact with the Venus atmosphere. So basically, just instead of the Earth atmosphere, you have the neutral atmosphere model. You replace with the Venus atmosphere, right? And other than that, all the equation would be the same. So next slide. This is to compare the situation with Earth and Venus. The blue curve is for the Earth, and the red curve is for the Venus. The idea is to say that, basic idea is to say that because Venus has a much thicker atmosphere, as you know, therefore the meteor coming in, they would generate heat and so say reduce their velocity and all that. So therefore they would burn up at higher altitude than in case of the Earth. Yeah, but then for all those, the equations are more or less the same. Yeah. So that is what we know about, the meteor abrasion in Venus atmosphere. But important thing is that will also bring heavy elements, metallic elements to Venus atmosphere, just like in the case of Earth. Yeah. The next one. Well, the other thing that we watch, say, foreign stars on the ground, right, and make a wish. But how about in space? And this two picture is that in terms of the International Space Station as an experiment called watching the meteor stream from the space station. Next time you have your own space station, please do the same thing. And this is one example saying how you see this meteor, the streak, caused by the meteor inflow. The interesting thing that for colleagues here at PRL, and in particular for Professor Yajush Barberi, is that there are studies saying that sometimes people might confuse the meteor inflow with lightning. But of course, for Venus, the problem is we have not that much lightning, yeah, and also you can tell the lightning from meteor inflow from other means. But this paper, this picture comes from another paper making a proposal kind of to ESA, because ESA is going to have a Venus mission. So their argument is that with their orbiter to Venus, can you also equip it with a camera, so it could count the meteors, info that way, as a dust detector that way. Of course, you can do it night side, day side, you can see something else. I think that's a very interesting idea. Maybe the PRL colleagues working on the Venus mission could think about that. It's not very expensive, right? But it's very interesting. Next slide. So this is just to say that that's the paper I mentioned, by Crystal et al. And you can read the paper in detail. But the argument is just very simple, saying that if you have a camera, use it, and if you're interested, make sure that you argue for a camera, to put on the Venus orbiter, and that is one scientific objective you can count on. The next slide. Okay, so we talk about meteor inflow, at Venus, and this is the picture that say that okay, the meteor burn up and they high up at 100 kilometers, but below, you have this denser and denser atmosphere. The interesting part is that in the middle, about 50 kilometers, there, that's what attention has been given recently. Next slide. Once again, for Venus, we know that this is from radar. The surface is kind of from geological active, and the plate tectonic is very interesting. Yeah, because it's very different from the Earth. So for planetary geologists, this is a godsend, to them, and because they might tell you how the Earth behaves, long times before the plate tectonics start to operate. And however, to do that, you need to see through the thick atmosphere. Actually, this picture is taken by radar, but usually you use optical camera. That's what you see in the next slide. Yeah, you just see this, which we call the super rotating. It's a solar wind, rotating very fast. I think 4 days, even though Venus hardly moving, is moving very slowly. So we call that super rotating wind. and the Japanese Akatsuki mission did a wonderful job in deciphering the dynamic of the cloud or the weather pattern there. Next slide. And what happened was that sometime in 2017, there was a paper by Sanjay Remai, and he had been studying Venus for a long time, since the early 80s, I mean, I really admired him. And in this paper, he because then you have more data, more data from Venus, pioneer Venus, and so to say, several years imaging of the cloud and so on, and also a different wavelength. And then in this paper, they point out that there's some absorption, I mean, wavelength absorption feature could not be totally explained, so understood, and unless there's something else in there, in the atmosphere. So then they start to speculate. I would say not speculate, but rather to speculate is not a good word, but rather start to make the how to say it, proposal, saying that the hypothesis. So next slide. The hypothesis they make, which I was later, if I have time, I would tell you that. Sorry.
10月6号中秋节的用餐，如果未登记的话，27号最后一天的哦，趁着现在还有2天时间，尽快报名参加10月6号中秋节的共荣晚会。祝大家平安喜乐，有美好的夜晚，明天再见啦，晚安。
Hello. Jess, is there any issue? You are muted. Jess? You are muted. Is there any issue?
I'm sorry.
We are
We can't hear you.
Yeah, so Professor Wing-Huen is also
muted.
Yeah.
Yeah, he is.
Bosit, can we unmute?
Actually,
no, we
I
cannot.
am muted, but I'm seeing Professor Wing-Hup's audio is not
Can you hear me
coming to
now?
us.
Can you hear me?
Yes, now it's okay.
Time.
All right, so can I continue?
Yes.
Because
yes.
just a minute
Yeah,
ago,
Jess may be sharing, then we can.
there was announcement from my building management, so requesting people to bring garbage out, to be corrected. So sorry. So I was saying that this idea that at about 50 kilometer altitude, there the pressure of the atmosphere and also the temperature atmosphere is comparable to what we have on Earth at the surface. Yeah. So this point was noted before, but then the Sanjay bring it up again, saying that, look, there's something special, if something interesting happening, it could well be there. So they once this paper come out, in 2017. Now, I remember that perhaps the paper came out in the right time, because if they said something like this before 1995, people would say that you're crazy, you're crackpots, And now that today, when they said this, everybody welcome, say, oh, you're a genius. you told us something very interesting. Yeah. And then next slide. So they in there they say, oh, how about there what things we have not thought about, what could be interesting, and they talk about metal organic chemistry, in that paper. Actually, I heard about metal organic chemistry, of course, in some other place, but in the context planetary science, this was in their paper. And then why the metal organic chemistry is important, because it does something, you know, can serve as a center for formation of other molecules, which could be of biogenetic, you know, interest, so to say. So when they have this paper, and in the paper they add another cartoon, which really raised people's attention. The next one. Say that they drew a cartoon like this, you know, they even add a number of microbes, you know, into the region where it's a 50 kilometer. Yeah. And the idea is that perhaps, you know, there, you know, you have some large molecule that even have a biogenic significance. Then in later, just happened that in 2020, next slide. In Hawaii, they have the JCMT submillimeter telescope. A team used that, the British team used that to look at Venus, and they found a signature, the absorption signature about where they claimed it to be pH-free, phosphorus. And from the absorption signature, they claimed that that is about 20 ppb, 20 parts per billion, even though it's tiny in proportion. But however, the pH-free is very unstable. Yeah, to maintain that level means that you have something, you know, some mechanism to maintain it. So could there be a layer, as you know, on the right hand side, the figure, you have a pH-free layer, you know, surrounding surrounding Venus. If true, that means something else must be producing it. And ordinarily, naturally, you do not produce this except that you have a biomechanism. So of course that come out as a big news. And then the next slide. But subsequently, you know, people then have the idea that now then we could go to Venus to take a sample, right? And the target is at this 50 kilometer. And they even have a name for this mission. They call it, next slide. Sorry, I had jumped ahead, but the next slide, please. Yeah. So when the 2020 JCMT detection was announced, that the several follow-up observation was done, well done, and as today, you know, a very low, much lower limit was given to the pH-free. So therefore, the detection is not confirmed, so to say, you know. So therefore, it might not be there. But it does not say that something interesting is not there, but that's that the pH-free detection signature was not confirmed by more sensitive, even like by using ELMA. Next slide. Then it does not, how to say, stop people from thinking, yeah. And so immediately, just like the case of the Martian meteorite, they found this micro fossil, right, on the surface. Immediately start a new wave of Mars orbiter program, and this almost the same meaning. And then people talk about how to go there, you know, to sample, because it's very acidic, that region, filled as O2 and sulfide and so on. So you talk about balloon, big balloon, and sometimes even using a glider. Yeah. For the balloon, next slide. Their mission was was named called Valentine, even, you know, so good, such a Valentine mission. And the idea is that you put a balloon and you drop down, right, and take just a very short time, because that place is dangerous, very erosive. You collect things and you quickly, you know, get back up. Yeah. And perhaps if not enough, you try again, that kind of thing. So that's the idea of the Valentine mission. Yeah. Okay, now next slide. Yeah, this one. And then there's a number of new missions to Venus announced a couple of years ago, and including NASA's Da Vinci and Veritas, that you know, and ESA's Envision, and and yours, VOM, yeah. And in principle, they are all radar set orbiter, am I correct? Yeah, because you want to get a much better, highest resolution geological images of Venus. But then there are also, interest in this atmospheric cloud deck. So there's a mission announced by the Chinese space agency CNSA. They have a mission called Voice. Originally, it was just like what everybody trying to do, namely to do a radar imager. But then in the middle of being approval, being reviewed, they add the sample return component to it. So now that because the Chinese, they say they want to focus on the habitability of the solar system. And because of Venus, because of the story, they think that they should go to Venus. Next slide. So this is basically what they want to do as far as I can find, targets the 30 to 50 kilometer. And you pick up the sample ideas to analyze the meteoric inclusions. Yeah, they think that anything solid particle, part of them will have come from a meteor. Yeah, and isotope telling you the origin, right? And then the microphysics of this aerosol, which is interesting, causing the thick atmosphere. And then putting their search for trace organics. Perhaps there's organic molecules. The next slide. So if I have this, what I have prepared earlier, saying that I talk about surgical light and talk about the interesting part about the Venus cloud depth between 50 kilometer and a little bit high up, right? And then about this new initiative in trying to do a kind of interesting kind of sample return, but so to scoop up the gas and dust particle in it and bring home. Do I have still some 10 minutes or so, or 5 minutes or so? If I have,
Yes.
I could just show a few more slides, which are even more speculative than what I just said.
Yes.
Since this is, I think it's a kind of informal, not a very strict scientific talk. So earlier, I know that you're planning a dust detector for the Venus orbiter. I hope so. Yeah. That's why I think that the detecting the dust or trying to image the meteor info on Venus would be a very interesting part. But the idea is that coming back, you say that those metals brought in by the meteors, they provide certain, so say, essential key element for possible, possibility of life in this, and that's called organometallic photochemistry. And if you check, that actually is a very interesting thing because it can kind of shield the UV light a little bit, and hence allowing the large macro molecules, so to say, to survive. Yeah. So the keyword is that if you go to Venus, you have to be good at organic metallic photochemistry. Next one. Next slide. There, because you get iron, you get phosphorus, you get carbon, those complexes, you produce this cluster kind of thing, and there you see that they would lead to, be causing a catalytic, they could have a catalytic mechanism allowing how to say it, normal kind of molecules would not have been produced, but if you put them in there, they must be there, by the way, because you have meteor, right, coming in, bringing metals in there, and having the CO2, adding with CO2, you produce FeCO, FeCO, that kind of thing, and so if you go there, you better look out for them, yeah. And the idea is that with them, then the next step is to say how it has to do with life, is that a one step leading to the possibility of biogenic microorganism. The next one. So in a way, you could call yourself going to Venus and treating it as a cosmic laboratory. Cosmic laboratory in the sense that not just for planets, for cloud, but rather even for life, for original life to that extent, because this is some kind of thing that we have never thought about, because of some, I would say, interesting coincidence, you discover something which then disappear, but that raise your interest, and think about something that different. So next slide. So we always say that we talk about when we say, oh, life as we know it, or life as we know. How about life as we don't know, right? I mean, Carl Sagan would love to say that too. Yeah, life as we don't know, because there are things that in the universe, there are regions where it's highly toxic, acidic, and where some other chemistry would take over, and very different thing might have appear. But then if you say you're looking for possibility of life, and Venus is one place. I think that you're going to Titan or going to Europa. I think it's rather mundane compared with Venus, because there you have water, right? You know what they are. You're going there just to track the origin of life as we know. But here you're doing something that you completely don't know. Okay, next one. So then we goes back to in fact the Venus cloud life hypothesis is started from Arrhenius, the famous Arrhenius, who have this Arrhenius equation, yeah, and back in 1918, yeah. But then down the way, off and on, people pick up again, and most notably is Carl Sagan, yeah. And then later on, after 2020, of course, there's much more attention given to this hypothesis. Yeah, even though, as I said, even though the signature might not be there, but however, they raise the interest of people thinking in a different direction, using Venus as a cosmic laboratory. So next one. Now Sagan is interesting in the sense that he talked about, because usually when I give a class to students, I say for exoplanet for life, you must look for up planets with a solid surface for you to step your foot on, right? But Sagan, long before in 1976, he teamed up with Peter Salpeter, had this hypothesis saying that for gas planet like Jupiter, actually he talked about Jupiter in particular. He talked about in the thick atmosphere of Jupiter, which is made of hydrogen, right, and helium. But there still he think about having organism, floating, or just following the convection pattern, up and down, and half intelligent, so to say. And then such kind of cloud-based life, how's the ecosystem, later on, then being applied to Venus, of course. Next slide. So this is the cartoon saying that how in this, in this very convective cloud of Jupiter, that you have this kind of things, and the next slide. And the Sagan and Salpeter in their paper even use some simple argument, I think, but very solid arguments, say where things could happen. Yeah. Next slide. So imagine that it's more or less like in the ocean. You have jellyfish, up and down. You have clouds of jellyfish moving. So maybe that's this kind of thing that triggered their imagination. Yeah. So life in the atmosphere of gas world, we find so many of them now today. Then you start to wonder, was something like that might happen, right? Okay, the next one. I think maybe even the very last one. Yes. So I think that it might be good, if someone, I hope that in India would think about the question about life in the atmosphere of gaseous worlds, because you have different kinds, different conditions, and then just by imagination, by logic, by physics, you can explore the possibility of life, in very different situation that we are used to. I think that is all I have, right? Okay, thank you for your listening. I think that you need a lot of patience to finish my talk. Yeah, thank you.
So thank you, Professor Wing, for very interesting presentation. Now I invite my colleague, Professor Vansil, to handle the question answer session. Professor Varma.
Yeah, thank you, Lukesh. Thank you, Professor If, for the wonderful talk and why dust is important and how it affects the Venus atmosphere and what are the directions ahead. And Professor If, now I request if you can take some questions. First, we will take questions from our audience from the WebEx. So anybody who's interested to ask can please raise their hands or unmute themselves.
Well, your first question, usually I get answer, say, I don't know, because life as we don't know.
Yeah, there are many unanswered questions, but the ones which you can actually answer. So I see Professor Jayesh Pabari. Can you please ask your question?
Yeah, it's very interesting and nice, talk, and multidisciplinary ideas and hypotheses are brought. I'm learning. If you can reiterate those things, like we think of the zodiacal dust cloud as a source or reservoir. The dust is coming to the atmosphere, probably could leave pH 3 or pH and like that, and those samples could be tested in the laboratory. So probably we think of the life which has been carried by, or the ingredients of the life is carried by the dust from the zodiacal cloud. Is that indication or hypothesis? Can you explain one more time, maybe?
Well, you're even more fast-fetched. You're talking about life in the zodiacal light.
Or the life could be in the Venusian atmosphere itself.
Now,
so like some of the ingredients are brought by the dust.
I think that's, we know that in 30, 40 kilometers above the Earth's surface, we find the microbe, right? Yeah, floating there. Of course, they were brought from the surface, but they've been there, survived there, and they turn out to be UV resistant, cosmic ray radiation resistant, for them to survive there. But I think they come from the Earth. Then I don't, and of course we are thinking that we are trying to make the case. We are trying to make case for Professor Yayish Babare that everything have to come from the dust, and other ways that for the Venus, the volcano, that they emit the gas. Of course, they also carry metallic element. They could also been raised into the atmosphere. Yeah, partly could have come from that. So that's why maybe the having the Chinese might be right that when they pick up those samples, they want to look at the isotope, composition. Yeah, that's one important part. And then telling that if they're aerosols, what kind of mechanism they might have been produced, what kind of ingredient they might have been produced.
Thank you, Professor.
Okay, there is a question by Anchal Sahu. Anchal, can you unmute yourself? Anchal? Okay, I think
I cannot hear that.
Yeah, I will not be unable to unmute herself. So, meantime, I'll ask you this question. We are talking about the meteoritic ablation through the dust. Now, the point is, even for the Martian atmosphere, it was long established that we do have this meteoritic layer. And now this debate has again started whether it is really due to, the meteorite. So, I mean, why do we have this ambiguity? I mean, are we not certain that yes, it is the dust which is ablating there?
Can you say state the question again?
No, my question is that, the dust, it forms this meteoritic layer in the ionosphere lower down, right? Especially for Mars, and even we understand for Venus. And this was sort of vetoed many years ago, that we observed that also. But now we believe that it may not be from this source. So why is it that? I mean, we don't have enough evidences for that, or how we don't understand it properly? We are coming back as a question for that.
So you're talking about the source of the zodiacal light, the distribution of zodiacal light?
No, the ionization at the lower level in the ionosphere due to dust. Is it due to meteoroids or not? That is the question.
No, of course, not completely, not completely. Yeah, not completely.
Exactly. So, what are the kind of observations that we can have which can convince us either way? Is it the source or not?
Well, because here you have a convenient possibility, which is you can look at the ionosphere during the meteor stream, at least for Earth, and see how that would affect the ionosphere, right? During meteor stream or during quiet time.
Right.
Yeah. And the lower part of the atmosphere, the ionization partly could come from cosmic rays, energetic cosmic rays, and that should also show some solar modulation effect. It's not simple, but I think that someone here at the PIA also studying the effect of cosmic ray intensity, the correlation with the cloud, right? The atmospheric cloud, saying that because saying that when you have a high solar cosmic intensity in the solar system, the Earth cloud would have different coverage, and that correlation was well studied by the Danish group some times ago. But I think that whether in India, there is another problem that you might have also people look at too. And that might also have an ionization effect.
Right.
Because it's the cloud, so it's very low down in the atmosphere, even below the.
Great, thank you. I suppose we don't have more questions from WebEx, so we can take some more questions from the YouTube. There are some lot of audience which are listening to us on YouTube.
Professor Varun, I think Achal is trying to join. I think I see her joining in two systems, so we can go back to her if she's.
Achal, can you unmute yourself?
Yes, sir. Yes, sir. Am I audible?
Yes, please ask your
Yes.
question.
So very nice and interesting talk, and I'm Achal, and I'm working under Jay sir on interplanetary dust dynamics and flux in inner solar system. And I have two questions basically. First, that you told about this dust-free zone and all. So since PSP went down to few solar radii where the dust and plasma environment both are very intense, so the measured voltage signals by the field's experiment could arise from both dust impacts as well as the solar wind particle interactions. So how can we distinguish that the observed voltage is due to dust impacts and rather than solar wind interactions? And second question is that in the absence of returned samples, how can we discriminate the asteroidal versus cometary sources for IDPs in the zodiacal dust cloud? Like if we would have samples, then we can find out using the composition. But without that, how can we find the source of the IDP?
You said you're a graduate student?
Yeah, she's doing a PhD in our group with Professor Jayesh Pabari.
And who's her professor?
Professor Pabari, Jayesh Pabari.
I must tell him that she is a very good student. So you asked two good questions.
Yes.
The first one about that, I mentioned that the how can you tell the signals caused by dust or by throwing? You say, yeah,
Yes.
because the usually they talk about this hitting the signal, hitting the antenna coming from the nano dust particle. Yeah, they're tiny particle. And somehow they could determine that from laboratory calibration could tell the energy involved, and even maybe some inclination on the some idea on the mass. So therefore they could tell the velocity. The reason being that only so that the energy is big enough that they produce a characteristic signal, electromagnetic signal. Yeah, and
Yes, sir.
that effect is kind of, I mean, as far as I can tell, is kind of documented or like a doctrine, they're indoctrinated, saying that, oh, when you see this kind of signal, and solar wind particle is tiny, and even though moving at 400 kilometers per second, cannot produce such a strong signal. Yeah, that's one thing. What was the other question? I think interesting question. Remind me again.
So other question is that in the absence of return samples, how can we discriminate the asteroidal and cometary sources for IDPs in the zodiacal cloud?
Well, this is there is I don't say it's a controversy, but it's an interesting thing that Professor Yayish Babari should tell you that because he has a number of papers on that. Juno spacecraft went through the 2AU from the Earth to Jupiter, and Juno does not have a dust detector, but then they could count dust by having the impact on the panel, on the spacecraft panel. Yeah. So using the huge spacecraft panel, they could count. Then it was published saying that they originally you expect there was a famous paper saying that the zodiacal light indeed produced in the main belt, asteroid belt, between 2AU and 3AU. Yeah. So expect that there you see more dust impact, right? As the spacecraft went through 2 or 3AU. But then when they compare and compare from 1AU to 2AU to 3AU, they found that between 2 and 3AU, the dust impact rate is far weaker, comparatively weaker, I would say, than what they have found as they cross the orbit in the vicinity of Mars. So that's a very interesting result and strange result, in fact, that the origin of the zodiacal light originated in the Mars zone. Yeah, and we tried to do some calculation, but we could not come to a quick conclusion that having this thinking that if you have produced a small dust particle and allowing that they be drift inward by quantum opposite effect, and somehow by as they go through the Mars orbit, somehow by resonant effect they will be piled up at the Mars orbit vicinity, but turns out not to be easy. Yeah, and Professor Yayish Babari should give a talk, yeah, about that, because he has a very interesting idea saying that everything comes out from Phobos, right? Yeah.
Yeah, thank you. We'll consider sometime, sir.
Thank you, Professor. There is a question by Swati Ravi Prakash. Can you unmute yourself, please? Swati Ravi Prakash. Okay, I think not able to unmute. So, Lokesh, can we have questions from YouTube? I don't think there is.
Yeah. Okay. So I'll have to go to my colleague, Dr. Durga. So, Dr. Durga, can you tell us if there is any question from YouTube? Hello. I think he's not able to hear us. So yeah, we can end the.
Am I audible? I'm Swati.
Yeah.
Okay,
So,
Swati.
yeah.
Swati, can you introduce yourself and ask the question?
Yes, sir. Good evening, Professor. I am Swati Ravi Prakash from St. Joseph's University. Currently, I'm working on exoplanet similarity indexing to solar system objects that like Venus and Mars, and I'm doing a comparative habitability analysis. So when we talk about habitability, what we're also trying to do is make the definition as cohesive as possible, right? Because usually we follow a very Earth-centric approach to habitability definitions. So we're also trying to um, come up with something that can include the definitions of life as we do not know it. So I also have two questions, sir. My first question is, could Venus potentially be hosting organisms that are not fully evolved, but instead are some form of proto-life or prebiotic chemistry? And if that is the case, how might the reported presence of phosphine in the atmosphere fit into this picture? Is it as a byproduct of exotic chemistry rather than a true biosignature?
That's your question. I think that phosphine is important, because that is important for the life as we know it. Yeah.
Yes, sir.
And if it isn't, so therefore you could use other things. So that is something that, like actually Sanjay Lame, he talked about that there's still something, some molecules in the atmosphere of Venus that absorbing the solar radiation. However, he could not find, the right kind of, molecules to do that job. Yeah. And in fact, if you look at the papers, they even seen that those pattern could be changing with time, because those are experts. So they see tiny things that to be very significant. Yeah, but those are very inspiring, work. Yeah. So I think that the seems that today the conclusion is that the phosphine signature is not there. Yeah. But it doesn't mean that some other things that isn't there. Yeah.
Yes, sir. I have another small question. Traditionally, the model that we use for exoplanet habitability is the liquid water on the surface idea, right? Because Venus challenges this. How can studying its atmosphere, including ambiguous signals like phosphine presence, help us broaden our definition of habitability and maybe even refine how we assess potentially habitable exoplanets?
There's one astronomer that I sometime before I talked to, which was Toby Owen. He was also very interested in astrobiology, and he used to say that in a place where it's very hot, temperature very hot, then you could have a silicate-based, life, not carbon-based life. So, I mean, for some place like a hot Jupiter, very hot, even hot super Earth, and the chemistry will be different. And unfortunately, I'm no Carl Sagan. If I were him, I would answer your question beautifully. But now I could only hide. Maybe Anil could interject something. He always have good ideas.
Thank you so much, sir.
Sorry, I mean your question is very welcome. If I would be very happy to learn from you actually.
So I think we don't have any more questions. So Professor, thank you so much for answering the questions, and I hope many of the discussions and questions which were discussed in your talk, hopefully some of these may be answered by our future Indian Venus mission. So with that, I hand over to Lokesh Sahu.
Yeah, thank you, Professor Varun, for very nicely handling this session. So just we are about to conclude, and for that I invite my colleague, Dr. Vinit Goswami. Vinit. You are muted. Vinit, we are not able to hear you.
Can you hear me now?
Meanwhile, Dr. Bhusit. Hello.
Well, my mic is open now.
Yeah, can you give us concluding remark?
Yeah.
Oh
Vinit
yeah,
is
and
able
I
to
want to
speak
thank
now.
you very much. Because the giving such a talk is very challenging because you are talking about things I have no idea at all. But then I learned much from you, and then I have forgotten to say in my talk that I would very much like to join your mission.
Yeah, thank you. Dr. Bhusi?
Yeah. Vinit, are you able to? No, I think Vinit is
No. So,
not
please.
possible.
Yeah,
Yeah.
I request Dr. Bhusi.
So Vinit, I take over. Thank you, Professor Ip, for such an interesting lecture and also the question answer session. I would like to thank on behalf of the PRL का Amrut Vyakhyaan committee as well as the Venus SC 2025 to Professor Ip for his accepting the invitation and delivering this Vyakhyaan. Would like to thank our director, Professor Anil Bhardwaj, Dean, Professor Pallam Raju, and our Vyakhyaan committee for their constant encouragement and efforts in running this Vyakhyaan series so successfully all these years. Best wishes to all the participants of this Venus conference and Navratri festival greetings to all of you. With this, we conclude today's session for the Vyakhyaan as well as Venus, if I am correct, Jayesh bhai?
Yeah, we are concluding Venus day 1 also.
Yes. So see you, Venus participants can see each other tomorrow, and for Vyakhyaan, we'll meet next month once again. Till then, take care. Good night. Thank you.
Thank you.
Hello.
Good night. Bye-bye. Thank you.
Take care.